Okay, thank you, Aaron. So, thank you very much for being here. Thank you, Natasha, and the other organizers for the invitation. So, the talk of today is about making two-dimensional electron gases ferroelectric and even multiferroic, which, as I will try to explain, is a little bit, in principle, should be impossible. It's like impossible materials because, in principle, you cannot have a metal. Two-dimensional electron gases are, of course, metals. That is at the same time a ferroelectric. So the work is mostly the PhD work from Julien Bréhin, who graduated last year and is now in Nogune in San Sebastian. And this is a collaboration with a number of people, including the group of Marco Saluzzo in Naples, Laurent Village and Philippe Patané in Grenoble, and Cynthia Piamontese as well at PSI, and Julien Varignon also from theoretical calculations. Okay, so ferroelectric metals. So as I was trying to say, so these are in principle contraindicated materials because ferroelectricity typically needs to occur in a material that is an insulator, and that has no conductivity because when you have free electrons, they will screen the basically the electrostatic forces that will couple the dipoles between the ions. So ferroelectric metals should not exist. But as very often in condensed matter, it's always interesting to scratch a little bit below the surface and dig a little bit deeper. And I think that was one of the strategies for magnetic ferroelectric multiferroics, where there were actually very few, as mentioned by in a famous paper by Nicolas Pauling, but people started to scratch and discovered that there were actually many ways to make magnetic that would be ferroelectric, and there's now many different families of multiferroics, while initially it was thought that these properties was magnetism and ferroelectricity were kind of mutually exclusive. So ferroelectric metals were first mentioned by P.W. Anderson in that paper from 1965, referring to this material, which I think is non-centrosymmetric, and has a phase transition which resembles that of ferroelectric, some ferroelectric materials. This was basically stayed relatively unnoticed for many years, and I think this paper is actually quite interesting in this, this drive to discover ferroelectric metals. So this author took barium titanate, which is, the most canonical ferroelectric. Just as a reminder, you can see here the sequence of ferroelectric phase transition. So there's some structural phase transition from rhombohedral, orthorhombic to tetragonal to cubic phase. The cubic phase is the non-ferroelectric phase at high temperature. You have, changes in the spontaneous polarization and peaks in the dielectric constants at all these temperatures. And what this author did is he actually took single crystals of barium titanate and he annealed them in vacuum to introduce oxidation vacancies. And in this titanate, it's very well known in strontium titanate that if you create oxidation vacancies, they will provide electrons which will dope the materials and make it metallic. This works very well in strontium titanate, and actually it works as well in barium titanate. So this is how you make, you introduce electrons, you dope the system. And you can see here the resistivity versus temperature for different crystals with different amounts of oxidation vacancies. And you can see that where they initially they're pretty insulating, but at close to room temperature, they have lower and lower resistivities as you dope more electrons. And even the most dopes are almost completely metallic. What is interesting is that you can see these very sharp kinks and steps which actually occur at these phase transitions. So the material is very conductive, even metallic, but it kind of remembers that it has this sequence of phase transition, which is characteristic of its ferroelectric phase. So you could say that this is a ferroelectric metal, but because it is really metallic, you cannot apply an electric field and measure polarization or switch polarizations. You cannot switch the other parameter. But this was a very interesting first result. A few years later, there was this report in Nature Materials of lithium osmide, which is very similar to lithium niobate, which is another very characteristic, very well-known ferroelectric. And in ferroelectric, you have this phase transition as well, structural phase transition, where the material is cubic at high temperature. So the C and A parameters are the same, but below a certain temperature, typically the Curie temperature, you have a lowering of symmetry, and then the C over A split. So this is almost exactly identical to what you would see in lithium niobate. But now this compound, lithium osmate, is indeed a metal. Okay, so the resistivity shows this metallic behavior, and there's a strong kink here at the phase transition. And doing advanced TEM, these authors were able to show that in the ferroelectric phase, there's actually some polar displacements of the atoms, which build up to create a polarization. But again, because the material as a whole is a 3D metal, you can never apply an electric field to switch the polarization. So you cannot really prove that the material is ferroelectric. So how could you have metallicity and ferroelectricity and be able to apply electric field and switch the polarization? Because that's what you need to do to show that your system is ferroelectric. You need to show that you have at least two stable, at zero electric field, two stable polarization state, okay? So for that, you need to, one way is to go to, okay. Okay, so to move to the to 2 dimensions, because in 2 dimensions you can hope that your electric field, which will penetrate your material over the Thomas Fermi screening length, will still be finite within the very thin low thickness of your material. So there will be an electric field in the material, and then you will be able maybe to switch the polarization. Okay, so this direction was perhaps the guiding principles for this couple of studies on this compound tungsten ditelluride. Here I'm showing you some PFM, piezo response force microscopy. That's one of the usual techniques that people use to characterize ferroelectricity. So you can collect these loops, which in principle should mimic the polarization loop. This is not perfect, I would say. That's completely very convincing evidence. This other paper is probably more interesting. This is conductance as a function of the perpendicular electric field applied to a flake of tungsten ditelluride. And you can see these very sharp switching peaks in the conductance at critical electric field, which could correspond to the corrosive electric field of the ferroelectric flake here. Okay, so coexistence perhaps here of ferroelectricity and metallicity with a coupling between the two. So our approach is different, but we of course want to go 2D to be able to work in this 2D regime where the thickness of the metallic slab will be comparable or thinner than the Thomas Fermi screening length. So we work with oxide-based 2-dimensional electron gases, and we start with strontium titanate, which is one of our favorite materials, and that of many people here in the audience. And then there's different ways that this material can be made ferroelectric. It's actually very close to being ferroelectric, so you can apply epitaxial strain. You can also replace oxygen 16 by oxygen 18, which is something that people in Japan have been working on quite a lot. Another way is to replace just 1% of the strontium ions by calcium. And then you have a ferroelectric, and then you can make it metallic as well. This was also discovered by Cameron Banya, who I think will be here next week. And another way, which in fact is the oldest approach, is to apply a large electric field. This was discovered in 1956. That's the oldest paper I could find. And then you can stabilize a metastable ferroelectric state. So basically, most of the work I will show will be working with calcium STO. So we start with the calcium STO single crystal, 1% or 2% of calcium. And then we grow something on top, aluminum or LAO. And then either through a redox process or from charge transfer, some polar catastrophic kind of scenario, the growth of this material on top of the calcium STO generates a 2-deg, like in usual LAO or aluminum STO. Okay. And then the question will be whether this 2-deg living in the ferroelectric material is itself ferroelectric. Okay, so I'm the first speaker talking about LASTO, so I will have a quick introduction about this. So this system was discovered by Hao Wang in 2004. Basically, it's a bilayer. I mean, it's a layer of LAO here on the right that you grow epitaxially on top of transform titanate. LAO is lanthanum aluminate. Each subplane of the perovskite in transform titanate is neutral, while in LAO it is charged. So in certain conditions, when you grow LAO on top of STO, basically you build up a potential which actually at a certain point the system has to find a way to lower the energy associated with this buildup, and electrons are transferred in this scenario from the valence band of the LAO to the conduction band of STO, and therefore forming a two-dimensional electron gas. Okay. So one point I want to mention here. So this is not fully accepted in the literature. There's some subtleties, but that's the so-called mainstream scenario of polar catastrophe. What is quite clear, and this is non-disputed in the community, is that this is some kind of almost triangular quantum well, and therefore here there's an electric field in the 2-deck. Okay, and that's very important because this electric field is going to push the cations in one direction, strontium and titanium, and the oxygens in the other directions, thereby creating electrical dipoles. Okay, so there are electrical dipoles here in the 2-deck regions, and the system is of course metallic. So this 2-deck is in fact a polar metal. Okay, it's also two-dimensional. We checked that a few years ago, or actually many years ago, using conducting IFM. But the point is that these 2-decks are polar 2D metals. Okay, they are not ferroelectric because the polar displacements cannot be switched. They are just set by the presence of the interface. Okay, but they are already polar. Okay, they are polar displacements which are more or less fixed. In addition to that, there are some free carriers. Okay, so the properties of these 2-decks are well known. There's pretty high mobility at low temperatures. It's superconducting at low temperature, and you can gate it because it's 2D and it sits on top of this STO, which has a very large dielectric constant. So electrostatic gating is very efficient. So you can tune the sheet resistance by orders of magnitude. You can tune in or out of the superconducting state by applying the gate, and also the all result from the group of Jean-Marc with collaboration with Marc Gabet here. Interestingly, for what I'm going to show in the next few slides, is the presence of a Rashba spin-orbit coupling, which was first evidence from these weak anti-localization measurements. And the Rashba coefficient, which is shown here, is a few tens of milli eV angstroms. It's not extremely large, but it's quite, let's say, substantial, has a strong gate dependence as well. Okay, so I'm going to say a few more words about the Rashba spin-orbit coupling. So this is a consequence of breaking of inversion symmetry in condensed matter in the presence of spin-orbit interaction. And this is the Rashba Hamiltonian that enters the Hamiltonian of the systems when these conditions are satisfied. This is the Rashba coefficient here that quantifies the amplitude of the effect. And you can see from this mixed product of the spin, momentum, and Z, which is the direction perpendicular, basically, that's the electric field perpendicular to the interface, that to minimize energy, you're going to want to have the spins and momentum perpendicular to each other. So this is so-called spin momentum locking. And this is going to break the degeneracy. And if you take a simple parabolic model, basically the Fermi surfaces are going to look like this with two circular contours, and at each point of the contour, the spin is going to be perpendicular to K. Okay, so the spins are kind of curling tangentially to the contours, and for one contour, the spins are curling clockwise. For the other, they're curling counterclockwise. For the dispersion, basically, this manifests as a shift in energy along K, so that's different from the Zeeman splitting, which is along the energy axis. Here, it's along K. And this is the Rashba coefficient is of course characterized by this shift in K, also the shift in E here. Okay, so that was proposed in the 80s by Emanuel Rashba, and a few years later, still in the former Soviet Union, another physicist called Edelstein ask what would happen now if you take such a rush bar system and you apply an electric field, or basically you inject a current in the rush bar system. Well, what happens is that very crudely, this will lead to a small shift of your Fermi contours, okay? And because of the spin momentum locking, shift of this outer contour will correspond to the generation. Basically, you will generate an extra density of blue spins, okay? And the blue spins are the spins pointing up, and you do the same for the inner contours. You will generate an extra density of down spins, the red spins. But this area is bigger than that area, so at the end of the day, you generate a finite spin density, okay? So you apply an electrical current in a non-magnetic system, and you generate a spin density with the spins transverse to the direction of the current. And these spins can then diffuse in a neighboring layer as a spin current, and so this is a way to transfer, basically to convert a charge current into a spin current, to do charge to spin conversion in a system which is not magnetic. So you can have you can get yourself a spin generator which is not magnetic, which can be quite nice. So that's a direct Edelstein effect, and you have also the reciprocal effect, which is the inverse Edelstein effects. And now you want to inject spins. So you can do that by different techniques. Electrically, you can use ferromagnetic resonance. This is called spin pumping. And as you do that, again, because of the spin momentum locking, the excess blue spins are going to shift the outer contour to the right, inner contour to the left. The shifting the contours corresponds to generating a charge currents. The shifts are again non-equivalent. So at the end of the day, you get yourself a spin to charge current converter. Okay, and this was discovered experimentally much later, actually by people from our lab in collaboration with SpinTech. So for this particular effect, the inverse Edelstein effect, by which you convert spin into charge, there's a useful figure of merit, and which has the unit of a length, because here you are generating a 2D charge current in the plane of the 2D egg, or the 2D. It can also occur at surface states of topological insulators, and you inject a 3D spin current. So these two currents don't have the same density, the same dimensions. So basically, this has the unit of a length. This is different from the spin Hall effect, where the spin Hall angle, the efficiency is a dimensionless quantity. And this inverse Edelstein length is proportional to the rush-bar coefficient and to the momentum relaxation time. Okay. So to maximize the effect, you want to have large rush-bar coefficients and high mobility systems typically. Okay, so these two decks can be actually pretty nice for this, because they have substantial rush-bar splittings and large mobilities, so they should produce some large effects. So this is a picture of our lab. Actually, the picture is not very good. Sorry about that, but this is to show you that we can grow materials by PLD. This is where we grow the LAO, for instance. Then we can transfer it. We can grow whatever on top, permalloy, aluminum, cobalt, and then we can check how everything goes at each step using XPS. We have also mask chamber. We can connect to a vacuum suitcase to go to the synchrotron to do RFS, for instance. So I told you at the beginning that there's two ways to make these two decks in STO. One is to grow LAO, which is the usual way, epitaxially by PLD. Another way, which is very much more convenient, is what was actually discovered by Andrés Santander from the University of Paris-Saclay, is to grow a thin layer of aluminum. This can be done by evaporation, MBE, or in our case, we use sputtering. So, and to check if, to show you that this is actually creating a 2-deck, we can use X-ray photoelectron spectroscopy. So we take a single crystal of strontium titanate, we put it into the XPS, and we measure the titanium 2p core levels. And this, the presence of these two peaks is typical of what you expect for stoichiometric titanium 4+ STO. Then we grow a bit of aluminum on top, and just 9 angstrom, and even it works if you go just 1 or 2 angstrom. And you see these strong shoulders, which corresponds to the reduction of STO, and then the titanium is mostly now here in this region 3+. Okay. So you are reducing the STO as you would do if you would anneal your crystal at high temperature in vacuum, but here you just do it at the at the very surface, and this means that you are populating the connection band of STO and therefore creating a 2-deck. So from the angle dependence, you can extract actually the thickness over which this reduced region extends, and it's typically you find about 1 or 2 nanometers. You can also check the aluminum. Here, probably it's not a very good example, but it's mostly reduced. In most cases, it's fully oxidized. The aluminum is fully oxidized into aluminum oxide. So basically, you grow aluminum, which is a metal, on top of STO, which is an insulator. And through this redox process, you basically transform aluminum into aluminum oxide, which is an insulator, and you make STO a metal. So okay, you transfer oxygens, and you transfer metallicity, if you wish. And then you get yourself a 2-deck. Yeah. Okay, so this is a TM image where on top of that we also grew permalloy, which we need for spin pumping experiments. And we see here that the aluminum is fully oxidized. You see the oxygen extends all the way into the aluminum layer, and the interface is actually pretty sharp. Okay. So still I'm not talking about ferroelectricity. I just want to lay the basis of this spin-to-charge conversion effects in STO, and then I will introduce ferroelectricity. Now let me explain to you how we do spin injection and we probe the spin-to-charge conversion from the STO2 deck using the inverse selection effect. So as I mentioned, we put permalloy on top of the 2 deck, and we use it for spin injection through FMR. So we put the sample in a microwave cavity, and then we scan the magnetic field. We have a fixed microwave frequency, and at some point we reach ferromagnetic resonance, and the magnetization starts to process. And as this happens, this is the ferromagnetic resonance signal at about 1,000 Gauss. And as we do that, basically, we are going to inject, so basically at ferromagnetic resonance, you inject a spin density, a spin current, basically flowing from the permalloy into the 2 deck, okay? You eject spin angular momentum from the permalloy. So it's injecting into the 2 deck, and if there is any spin-to-charge conversion, you're going to pick up a charge signal transverse to the direction of magnetization. So the magnetization is like this. And if you have voltage probes transverse to magnetization at ferromagnetic resonance, you should pick up a voltage. And this is exactly what we see. Okay? And this voltage should change sign if you reverse by 180 degrees the direction of the magnetization. And this is just what we see. Okay? So you really have spin-to-charge conversion. You change the direction of the spin you inject. You change the sign of the current that you pick up. So this is the inverse Friedrichs effect. Interestingly, we can compute the efficiency of the conversion. This is this figure of Mary Landa that I introduced a few minutes ago. And we find values which are extremely long, 25 nanometers. This is typically 1 order of magnitude higher than the best systems like bismuth silver or even alpha-tin topological insulators. And this is because even though this system has a relatively lower Rashba coefficient compared to these materials, the scattering times are much longer, especially at low temperature. And so because these 2 parameters enter the figure of merit, we end up having a pretty large efficiency. Okay. So one thing that is very peculiar about these 2 decks is they have a peculiar band structure. And as I will show you, this spin-to-charge conversion efficiency can be modulated by a gate. It can be modulated in amplitude. Okay. It can also be modulated in sign. So if you take a system for spin-to-charge conversion like platinum, spin-hole effect, the spin-hole angle, the efficiency of the conversion is basically set once and for all. You have set 10%. If you replace platinum by tantalum, you have minus 15%. Okay. This is set once and for all. In this system, you can change the amplitude and the sign of the efficiency of the conversion by the gate in the single material, and this is because of the peculiar electronic structure of the 2 decks. So let's have a look at this electronic structure in a little bit more detail. So these are our pulse measurements done in collaboration with the group of Felix Bomberger in Geneva, and these fits are tight binding fits from the group of Ingrid Martin in Halle. Okay, so you see here the Fermi surfaces. Basically, we have a number of circular Fermi surfaces, and these elliptical Fermi surfaces. Okay. In the dispersion, you can basically see here the lower lying, relatively low effective mass bands, and you have 1, 2, and 3 of them actually, because of the confinement in the 2 deck, and this corresponds to the XY orbitals. Okay, and higher in energy, you have these DXZ, YZ bands corresponding to these DXZ, YZ orbitals, which have a much higher effective mass, and you have these avoided crossings. Okay, and as the avoided crossings, you have a splitting of the bands. The Rashba splitting at the bottom of the band is actually very tiny. It's so tiny that we cannot see it, we cannot detect it experimentally. But if we fit the experimental RPS data with Hamiltonian, including the Rashba coefficients, we basically end up with this kind of splittings here at these avoided crossings. And that's where the Rashba coefficient is going to be the highest. So there was a couple of papers before this our results from theory that calculated that the Rashba coefficient of these bands is positive, and that the Rashba coefficient of that band is negative. Okay, so now you expect that when you are going to apply gate voltage, you're going to move the Fermi energy across the band structure, and at some point, while you may expect to see a variation and even a change of sign of the conversion efficiency if the Rashba coefficient is changing sign. In fact, things are even more complicated because of all these avoided crossings. And I don't want to go into much detail, but if you are interested, you can look at our paper here. This is basically the experimental variation of the spin-to-charge conversion efficiency that we measured experimentally. And you can see that we start with a large negative gate voltage with a positive efficiency, and then we have a negative efficiency, again positive, again negative, again positive. Okay. So many changes of sign, more than you would just guess by the change of the Rashba coefficient from one band character to the other orbital band character. But in fact, this can be explained by the theory, and these are the calculations of the spin-to-charge conversion efficiency for each set of band pairs. Okay, so you have the lower lying band, which is the purple one, which has a low positive efficiency. Then you have the next one is the green one, which is again always positive, and then this one, which immediately starts being negative, etc. And then you have the final blue one. So then, if you take the sum of all these contributions, basically you see this positive, negative contribution from the theory, which resemble very much what we measured. So we have a pretty good understanding of the spin-to-charge conversion physics in the systems based on the electronic band structure. Yes. Yeah. Okay, so here in STO you have you can move quite a lot because the dielectric constant is actually very high in STO. Okay, and actually you do two things here. This is an explanation within a rigid band model, which is some approximation, because also when you apply the gate voltage, you change a little bit the confinement in the 2 decks, so you also change the splitting between the bands. Okay, and we have Mark did some calculation on this paper to basically justify that it was still a relatively good approximation. But no, these results are actually very robust. We have seen them also using charge-to-spin conversion. We see the change of sign. Not so many changes of sign, but 2 changes of sign. And also other people, the group of Michel Viré has also seen a modulation. It doesn't reach a change of sign, but a modulation. Basically, everything is a little bit offset by a positive value. So this non-monotonic modulation is actually a pretty robust result now that have been reproduced by different groups. I think in principle, you're right, but here I think we are modulating by several tens of millieV because of the large dielectric constant and the low carrier densities in the 2 deck. Yeah.
When you put an electric field, do you see also that you can change the Rashba splitting effectively in your model? Because we influence the structure and the
Yeah.
symmetry?
Yes. So, so okay. So this would corresponds to changes of the electric field in the 2 deck because of the modulation. So this is a small modulation because the electric field in the 2 deck is on the order of several hundreds of millieV per nanometer. So that's a pretty large electric field, okay? Almost 1 eV per nanometer. Okay, that's the order of magnitude. So that's much higher than you can apply here, because here we apply, also the electric field is applied between the 2 deck and the, the back gate. So it's applied across the STO. So a little bit of the modulation occurs in the 2 deck, but that's probably a second order effect. The main driver for the change of the Rashba coefficients is the fact that you are moving the Fermi energy across the band structure. Okay. Yeah, Charles.
So in the spin orbit that you are showing, you show the band structure, it would appear at corners, right? Not at all around the circle, right? Where there is crossing of bands, right? So how does it change the picture you showed in the beginning?
Yeah, so that's a good point. So in fact, as I said, there is a small Rashba splitting here, but it's actually very, very tiny. It's, in terms of the Rashba coefficient, it's a few millieV angstrom, okay? It's very tiny. So the picture is more complicated because, of course, here you don't have these simple 2 parabolic bands. So in a way, you could say that all these Rashba coefficients that we are considering here are effective because, they also are the resultant of contribution for different bands. So it's not as a clean, textbook kind of picture. But, at least qualitatively, in terms of the energy dependence, I think if you look at the different, what happens when you put your Fermi energy in the different spots, you can more or less reason and understand this behavior and that behavior as well, actually. Yeah. So I don't know if this answers your question.
No, but maybe what I'm implying is that there might be some angular dependence with respect to where the corners are. So if you run the current like this,
yes.
like that, you might see something.
Yes. So that's an experiment that we have not done. We wanted to do it, but finally we didn't do it. And but I think Michel Viret in CA has done it. And now I don't remember what he found. Do you remember? Yeah, Jean-Marc? Yeah. It's isotropic, yes. Yeah, you're right. Yeah. I got you right. Yeah, now I remember. Yes, but okay. So I think there should be some anisotropy also from the spin, but the sign of the anisotropy that he found, I think he ascribed that the sign was opposite to the one they would expect from the spin. So there is one also from the spin, but he was ascribing it to orbital. Yeah, so that's also an interesting new direction because just like here, this is just spin Ehlstein, okay, but also we have some calculations with the group from Halle that there is also orbital Ehlstein effect, okay, of the orbital angular momentum, which is predicted to be up to 10 times higher. And then now the question is how you're going to be able to inject a large enough density of orbital angular momentum. As for spin, it's very easy. You can do spin pumping from permalloy. Now, what do? You need a ferromagnet that has a large orbital angular momentum contribution. And that's not so easy because typically they don't work very well for FMR. So that's something that we're also working on. Okay. Okay. So, Okay, so now let me introduce ferroelectricity. So I told you ferroelectricity can be introduced in STO by many ways. One is to, the oldest one, in fact, is to apply a large electric field to STO. And then you can stabilize some kind of metastable ferroelectric state. So here, that's the sample. We have a 2-DEG. We have a bottom baguette contact, baguette electrode. And we apply an electric field to measure the polarization. Okay. So at the beginning, we see a linear dependence. We have just a linear dielectric or slightly nonlinear dielectric. But actually, it depends on the samples. But in most of the samples, when we exceed a typical electric field value, which is on the order of 7 to 8 kilovolt per centimeter, then we have a very sharp transition to loops that look like this. So we have loops that look very ferroelectric, okay? And here I'm showing you for the experts the current loops where you see the clear switching current peaks here, okay? That really correspond to the switching of the polarization. And once you are in this state, basically it's there, it's stable, and it only goes away if you hit beyond the ferroelectric TC. So, so when you have established this state, you can study it as a function of temperature. You can see that it disappears at about maybe 50, 55 Kelvin. That's the remnant polarization as a function of temperature. And to show you, so these are some references that studied this in much more detail than we did. And just to show you that this is by no means anything new, I'm just overlaying exactly with the same axis this data from that paper from 1995. And you see that our data fall exactly on top of their data. So this is something very well known in STO. What is different in our experiment, of course, is that the top electrode, in our case, is a 2-DEG. So now we're going to try to see what happens to the 2-DEG when the STO underneath is ferroelectric, of course. So we perform this spin-to-charge conversion experiment, again using spin pumping in this sample where beforehand we apply large electric field to establish this ferroelectric state. And you can see here the spin-to-charge conversion signal, which initially is positive and relatively small. But then when we apply positive gates, it becomes large and negative. We go back to 0, it still stays large and negative. And now we go to minus 200 volts. It's large and positive, and then we go back to positive remnants, it still stays large and positive. So you can already see here that you have these two electrical remnant states with two different spin-to-charge conversion efficiencies. So we can do this excursion over the whole ferroelectric loop if you want, and we have this very nice hysteretic dependence of the charge, the produced charge current as a function of the gate. So we have a charge production by the inverse Sudeshtan effect that depends on the ferroelectric state. Okay, we have two different remnant states. And we can toggle between the states by applying positive or negative voltages and going back to 0. And we can study the difference between the amplitude of these positive and negative signals as a function of temperature. And we can see that the difference goes away at about 50 K, which is our ferroelectric TC. So we have a control of spin-to-charge conversion by ferroelectricity. And this is extremely interesting because I told you that in a rush-bar system, you have the possibility to generate, basically to detect a spin current. Okay, you convert a spin current into a charge current in a system which is not magnetic. And now you can do this with ferroelectric remnants, okay? And of course, in principle, you can do, and we have also shown this, we can do the reciprocal effect. You can inject a charge current, generate a spin current, and if you control it by ferroelectricity, basically you have spin current production, spin current detection, and non-volatility, just like you would have in a ferromagnet. But now you have it with a ferroelectric, which means that it's much easier to handle because you can manipulate it by electric field, and it can be done at much lower power, okay? So this is very interesting for devising new architectures for logic and memory that would operate at very low power. Okay, so we are actually working on this quite actively now. So what is the mechanism for this change of sign? Well, we don't have a definitive answer for that, but if you remember this curve that I showed you before, if we are applying the polarization, pulling the material in one or the other directions, we can imagine that we are going to be sitting at resonance in, for instance, in one of these two states where we have a positive or negative conversion efficiency. Okay, that's one possibility, although it's not completely decided. Okay. Okay, so this was about spin to charge conversion. We can also do charge to spin conversion. So this is in a way a little bit easier because we do this. Well, there are different ways to probe it. You can do spin torque, etc. But the approach that we are probing is just a simple magnetoresistance measurement, and we basically do angle-dependent measurements of the longitudinal resistance. Okay, so remember the direct electron effect. You apply a charge current, and you generate a spin density transverse to the charge current. Okay, so if you have a whole bar of your brush bar material, okay, you then apply a current along the channel, you will generate a transverse spin density. If now you measure the magnetoresistance and you change the direction of the magnetic field, it's quite natural to expect that when the magnetic field is parallel to this spin density that you generated with your current, you're going to get a different resistance than when your magnetic field is antiparallel. Okay, so this will give you a unidirectional magnetoresistance. Okay, and also this unidirectional magnetoresistance should change sign when you reverse the direction of the current, because if you reverse the direction of the current, you change the direction of the spin density. Okay, so this is so-called unidirectional magnetoresistance or bilinear magnetoresistance, because this effect is supposed to be linear with the magnetic field and linear with the electrical current. So this was formalized a little bit better by our colleague Anna Dierdal, and we published it in that paper. And at the end of the day, this is what the calculation suggests, that the resistivity is going to be made of two terms, and that's the term that we're interested in. Okay, this term is the unidirectional term. Okay, so it goes at the sine of the angle theta of the magnetic field. Okay, and it's proportional to the Rashba coefficient alpha, and it's linear with the current and the magnetic field. Okay. There is a second term which is due to scattering between the different contours of the Rashba system, which goes as the b square and is proportional cosine to theta. So it's a little bit like the AMR of ferromagnet typically, but of course its origin is very different. So we can do the measurements and extract the different terms, and we can then take the ratio between the amplitude of the two terms and use that to obtain an estimate of the Rashba coefficient. So you can do the measurements in DC or in AC. Okay, so in DC, if the unidirectional term is strong enough, you measure with positive or negative currents, and you can see on top of the dominant quadratic term, you see a shift, and that's the difference is actually due to the unidirectional term. So then you can separate out the two terms, and just looking here this is the cosine 2 theta terms. It should go like b square, okay? And this is the unidirectional term, which goes at the sine theta, as you can see here, okay? Sine theta, and it is linear with the magnetic field and linear with the current, as you expect. And these data here in the middle show how these depend. They both depend on the gate. Okay, they depend quite strongly on the gate in this STO system. And from the analysis of the gate dependencies, we can extract the Rashba coefficient as a function of the gate. And on the same devices, we measured also the weak anti-localization, did the analysis to extract the Rashba coefficient. So, So here you see the analysis from the weak anti-localization. And here, these are the data points from the BMR and QMR ratio. Okay, so we have a small range where they overlap and they give very similar results. But beyond that regime, we don't have any weak anti-localization anymore, and we can access the first point where we have a change of not a change of sign quite yet. Although in other systems we are able to see a change of sign with aluminum instead of LAO, but here we see a maximum and then a decrease. Okay. And this is the Lifshitz point. We know that that's basically the point at which you start to populate this band with a XZ, YZ character. We know that from the analysis of the Hall effect. And basically, if you come back to our band structure and we compute the Rashba coefficient from the band structure, we can see a relatively good agreement, again, between the data and the experiments. Yeah? To the speed of light.
Yeah, because that's the universal measure of the speed. The Rashba coefficient has dimensions of velocity.
Okay, so at this I'm not sure I can answer. No, the units are in milli eV angstrom. Okay, so you can compare this with.
Values are 10 to the minus 4 to, well, 10 to the minus 2 is too much, but 10 to the minus
Yeah.
So
you know the system with the highest Rashba coefficient have values on the order of eV angstrom. Okay, so that would correspond to maybe this 10 to the minus 4 that you're talking about. So this is about 2 orders of magnitude lower. Okay, so this is not a very, very high value for the Rashba coefficient. The beauty that you can modulate it with the gate in a way, and then you can harness it to do spin-to-charge conversion very efficiently because of the long scattering time. Sorry, I cannot give you a much better answer. Okay, so now let's again introduce ferroelectricity. I don't know, am I doing with time? Yes, okay. So it's until 10:10, right, Aaron? I think, yeah. So should be done by 10 to leave time for 10 minutes of questions. 10 o'clock, yeah. Okay, great, thank you. I think I will need that. Okay, so the other way that I mentioned at the beginning by which you can introduce ferroelectricity in STO is by substituting a little bit of the strontium ions by calcium, okay? And as little as 0.2% of calcium is enough to make STO ferroelectric. So this is shown in this phase diagram, which I copied from this paper from Cameron. 0.2% or 0.25% is where you start to have an onset of electricity. And then the TC kind of increases and eventually saturates at about 30-35 K beyond 2%. Okay. Just like in that early paper that I showed at the beginning as well of barium titanate, where you can anneal the crystal in vacuum, introduce oxygen vacancies, and then have some coupling between the ferroelectric phase transitions and that you see in the transport response. Cameron did just that with calcium STO, and you can see that the annealed samples where you have a lot of oxygen vacancies and therefore carriers have some kinks here, which in fact corresponds to the ferroelectric TC, okay? So you can see the ferroelectric TC in the transport response. Although again, because this is a 3D crystal, you cannot prove that the material is itself ferroelectric. Okay, so we bought calcium STO single crystals, and we use our favorite technique to grow the 2-deg on top, namely to grow aluminum, and we generate a 2-deg, and we can see that we have a nice metallic behavior with a kink at low temperature, and if we zoom in, we can see that it occurs at about 25, 27 K, which corresponds precisely to the ferroelectric TC. We can also measure the ferroelectric loops of the calcium STO using the 2-deg as our top electrode, and as a function of temperature, we see that we have a TC about maybe 25, 30 K. So it's a little bit the same as in the experiment from Cameron. Okay, so now these are again polarization loops measured with increasing maximum voltages, and this is all shifted for clarity for you to see everything better here as well. And here this is a sheet resistance measurement, so we measure the resistance for prod on the top as a function of the gate, and you can see that we have a hysteretic dependence of the resistance, okay? As you would expect, because the STO is not ferroelectric. If you do these experiments with just regular STO, except after the gate initialization, which always gives you some hysteresis, after that you always have let's say, a reversible gate dependence. Okay, you always fall on top of the same curve, no hysteresis. Here we have hysteresis, of course, because now we have this calcium and the material is ferroelectric. Okay, yeah, so that's a good point. So in principle here, the polarization should be along 110, and so what we probe here is the projection of the polarization, basically what is acting on the 2D, basically producing some ferroelectric field effect, is just the projection of the component of the polarization which is perpendicular to the interface. So yeah. There are some papers imaging domains at low temperature using crystal, using barrier effringence, for instance. But at some point we considered doing PFM at low temperature, but it's we thought it would kind of divert us a little bit from our main goals, so we didn't do it. But it would be interesting to do, yeah. Jean-Marc, yeah.
And the value of the polarization you get with the calcium doping is rather similar to what you were getting before.
Yeah, so it's a little bit smaller than what we had with the electric field induced for electricity in STO by factor maybe 2. And I think that's kind of consistent with the fact that the TC is also around 25-30, while in the other case we had maybe 50-55. In the titanates you have, give or take, a linear dependence between the TC and the polarization value. If you take barium titanate, which is 20, it has a polarization which is 20 times higher, and the TC which is 20 times higher as well, or 10 times, more or less. And PZT as well, like even 2-3 times higher. So yeah, so here what to actually, since you mentioned it, we did whole measurements at positive and negative resonance in these two states as well, and we estimated the carrier density, and we have a delta n of 5 10 to the 12. Okay, that's just 3% of the total carrier density. That's small, but that's actually, I mean, I didn't put it here, but that's, I think, close to 50% of what you would expect from the polarization. Okay, so that's relatively efficient gating. Okay, but of course you gate with a small polarization, so you cannot expect to have a very large effect. Okay, so coming back to this BMR, the BMR, that's the consequence of the direct Edelstein effect. So this is probably a reminder for what I've shown before. So if you apply a charge current, you have a transverse spin density, then you get this kind of BMR. If you reverse the charge current, the spin density is reversed as well, and so you have opposite sign for the BMR. Now what would be nice would be to be able to control the sign of the BMR, basically to the sign of the charge to spin conversion, spin generation, by a gate, okay, by a ferroelectric gate, by taking advantage of this possibility to switch the sign of the Rashba coefficient. So ideally in one case you would have this, and then without changing the sign of the current, you would change the sign of the Rashba coefficient, and then the spin density would be generated in the other directions, and as a result you would change the BMR. That would be telling you that you're switching the sign of the BMR, and so we've been working to do that, and we still are, and our best results so far are shown here. We basically have a modulation of the amplitude, not a full change of sign. Okay, basically this was sketched here. If you just have a modulation of the Rashba coefficient amplitude, you will just generate a smaller spin density, you will have a smaller BMR, and this is what we've seen. So we don't have yet a full reversal, but we are working on it. With the STO gate in the non-ferroelectric state, we were able to see a full change of sign. Not yet with at ferroelectric resonance with the ferroelectric 2DEX. Okay, so all right, so I'm moving to the last part of my talk, where I want now to introduce magnetism in the 2DEX, okay? To try to make them not only ferroelectric, but in fact multiferroic, okay? merging these two very interesting directions on which our group has been working on for many years. Okay, so in kind of a sketch, this is the case of simple LAO STU where you have no ferroelectricity, no magnetism. When you replace STU by calcium STU, you turn on ferroelectricity. And then, in fact, there was some interesting papers, notably by the group of Marco Saluzzo, in that paper in particular, where they introduced a thin layer of europium titanate between LAO and STU, and they were able to make magnetic 2-decks. And now we teamed up with them, and we tried to get the best of both worlds and generate ferroelectric and magnetic, in other words, multiferroic 2-decks. Okay, so these 2-decks are metallic. Okay, sorry. Okay, so let's have a look at the density of state, the DFT calculation that we did, the Julien Varignon did on this system. Okay, so you can see here the STO. This is the europium titanate, and this is LAO. So europium titanate, why did we choose that? Actually, why did Marco and Daniela in Naples choose this material? So europium titanate is an insulator, titanium 4+, okay? The magnetism comes from europium. Europium is magnet 2+, magnetic 4F7, and in the bulk, this compound is actually antiferromagnetic. When you dope it with lanthanum, you can make it ferromagnetic. Also with strain, you can make it ferromagnetic. So here the calculations tell us a number of things. First, so these are calculations density of state for P up and P down. Here we introduce ferroelectricity not by putting 1% of calcium STU, which would require gigantic supercells. We play the strain game. We apply a small strain which makes STU ferroelectric. And then we do calculations of the density of state for polarization up, polarization down. So in both cases, we see that we have a finite density of states. Here it's actually finite but very small. And so we have a 2-deck in both cases, but with a strong modulation of the expected modulation of the conductivity depending on the ferroelectric state. Then, what do we see in the presence of the europium titanate? So this is the magnetic moment. So the magnetic moment on the titanium is found to be finite in the europium titanate, but also in the first couple of layers in the transform titanate. Okay. So we have ourselves a magnetic 2-deck in principle from the DFT. And in addition, the polarization direction is going to strongly modulate by maybe 20-25% the value of the magnetic moment on the titanium. So we expect to have a magnetoelectric coupling. We modulate magnetism by ferroelectricity. In addition, so these are calculations of the displacements, the polar displacements of the titanium cations in the STO. So remember at the very beginning I insisted on the fact that in LAO STO, in the absence of ferroelectricity, you already have polar displacement of the cations because of the presence of the built-in electric field in the quantum one, in the 2-deck. Okay? So because you have a triangular potential profile. So these displacements are always going to be there as long as you have an interface. But here in addition, because the material is ferroelectric, we're going to have an additional contribution to this polar displacement, which is switchable. Okay, so we have a background which is non-switchable, which is due to the built-in electric field. And in addition, we have a modulation, which is going to be switchable. So this is, in fact, what this graph is showing. So suppose you would go very, very far away from the interface where there is no built-in electric field from the interface. In fact, this value would probably go somewhere here. This is for the polarization pointing up. So you have the polar displacement for the ferroelectric in one direction. And for the P-down state, you have this strictly symmetric with respect to the red one for the other polarization. But here, because we are getting closer to the interface, we have this built-in electric field that pushes both values towards one direction, biases them to the left. And because of the competition between conductivity and ferroelectricity, they tend to be closer together because the ferroelectricity tends to disappear Because if electricity had completely disappeared, this red and blue point will be exactly on top of each other, as they are here or here, because here there's no electricity. But here you see that in this region where the 2DEG is present, these first 2-3 unit planes, you have two different values of the polar displacements. Okay, this means that in this region where the 2DEG lives, we have two different values of the polar displacement. In other words, there are two different values of the polarization. In other words, the 2DEG should be ferroelectric, even in the presence of the carriers. Okay? So now, of course, the trick is to probe that experimentally. So to do that is actually very tricky because, you know, the usual way to measure precisely this polar displacement is to do TEM, but here we need to do TEM at very low temperature, and these polar displacements are very small. So it's very, very challenging. So we use another technique, a macroscopic technique, which is X-ray linear dichroism. So X-ray linear dichroism is based on X-ray absorption spectroscopy. You go to the synchrotron and you shine light, you excite core levels, and you basically do that with a linear polarization, horizontal or perpendicular. And therefore you probe the environment of the, in this case here, the titanium. Basically you probe the crystal field around the titanium ions. So in the case of STO, because of the built-in electric field in the STO2DEG, you have a finite X-ray linear dichroism because the titanium is not sitting in a symmetric environment because of the polar displacement due to the built-in electric field. So this is, in a way, if you don't look at it very carefully, this is exactly what you would see in the case of STO, and this was reported by many groups before. Here, this is on the case of calcium STO, and we did the experiment at different temperatures, and we see that above the TC of calcium STO at 40 K and below, we see a difference, which is the first indication that perhaps some modulation of this signal, which reflects the crystal splitting, is due to ferroelectricity. But the most important experiment is this one, where we did the experiment at low temperature at 2K as a function of the electric field. So we applied an electric field and we pulled the sample in the P up state or P down state, and we measured two different signals. Basically, we have two different crystal field environments in the electrical resonance for P up and P down. So we can do simulation of these signals, and we can end up with a picture that tells us that we have different polar displacements in the P up and the P down states. And this is exactly in line with what we were expecting from theory, and this is telling us that we have two polarization values in the 2DEG, depending on the at positive and negative electrical resonance. I forgot to mention that these experiments are performed in total electron yield mode, which is a mode in which you probe just the very first couple of nanometers on the top of your sample. Okay? Yeah. And if you don't do that, you probe, you know, the whole, I mean, the first, let's say, 10 or 100 nanometers of the sample, and then, of course, you cannot conclude on what happens in the 2DEG. Here, we're just probing the 2DEG alone. Okay, so we can also use X-ray magnetic circular dichroism to probe the magnetism, because you remember we are making magnetic 2DEGs here. And we have a nice signal, XMCD signal on the titanium, which tells us that we have magnetism in the 2DEG, and we have these nice hysteresis loops from XMCD, and similarly, we have similar results for europium. Okay, so we have ferroelectric 2DEGs and magnetic 2DEGs from this spectroscopic measurement. I'm going to skip this. And now we're going to look how we can probe these two properties in transport. So here we see the resistance versus temperature. Again, we see a kink at the TC. We measure the polarization loops, and we can measure the sheet resistance as a function of the ferroelectric polarization, as a function of the gate. We have a hysteretic behavior, as we expect, as I mentioned before. And we can measure the polarization as a function of temperature, the carrier density as a function of temperature. The difference between the two goes to 0 at the ferroelectric TC. So this modulation disappears at TC. It's really due to ferroelectricity. Let me skip that and come here. I can show this to you eventually if you are interested. Okay, so the Hall effect that we measure is mostly linear, but if you look carefully, you find that there's a sizable nonlinear contribution which comes from the anomalous Hall effect. Okay, and I can show you why we are sure that this is coming from the anomalous Hall effect, not from a two-band type of transport. So we can measure the anomalous Hall effect as a function of temperature after polling the sample up and after polling it down. And we see that the looks look a little bit similar, but the amplitude is actually a little bit different. And this one is maybe 10-20% higher, and this is shown here. The maximum amplitude, the TC seems to be more or less the same, but in the P-down state, we have a difference by maybe 15% compared to the up state. We have also different values of the magnetoresistance. And since I'm running out of time, I want to rush to this last slide, where we have measured the anomalous Hall effect as a function of the voltage sitting here in the positive saturated state, here at a positive remanence, negative saturated state, negative remanence. Okay, and you see a clear modulation of the anomalous Hall effect, which is reversible. Okay, so basically we are probing the influence of ferroelectricity on the magnetism by doing transport experiments in the metal. So we are doing magnetoelectric coupling in a multiferroic metal, which is something that, even though I've been working on multiferroic for 20 years, a few years ago I would never have believed would be possible. So we have this reproducible magnetoelectric coupling in this very interesting system, which is a multiferroic metal. Okay. So I'm coming to my conclusion. I'm sorry I had to rush through the last part of the slides. But actually, I've shown you that these two decks are extremely interesting for spin-orbitronics, for spin-to-charge interconversion. We can have a very rich physics due to the complex multi-band structure of the two decks. And by introducing ferroelectricity, we can have non-volatility in the modulation of the spin-to-charge and charge-to-spin conversion, which is opening an interesting perspective for being CMOS electronics. And introducing a couple of unit cells of europium titanate, we can even make these two-deck multiferroics, and we can therefore probe both the magnetism and the ferroelectricity and their coupling in the transport sector. And we expect also these samples to be superconducting, although we have not been able to demonstrate that yet. And so we expect to have a very broad range of couplings between physical properties of condensed matter in these fascinating systems. Okay, thank you very much.